So thanks for joining. Yeah, so let's get started. So real-life performance optimization is never like this. Even though you may observe one geometric property of this small picture from a kind of like a marketing initiative by a company called Alinea. They're a vendor of debuggers and profilers, and more in the high-performance computing arena. And this fell into my hands 2 years ago, and I thought this is just great because it would be so lovely if it would be like this. Even if you have these curves here, and you have this, nice car that I would love to have as well. But yeah, unfortunately, it's never that simple. So that's one of the motivations of my talk. It's more like this. So this is from Wikipedia. This is a map of the Odyssey. So Odysseus started over here in Troy, right? And then he made his way and finally at some point reached his goal, his family. And the thickness of the lines indicate the strength of his crew. So this is sometimes how I feel with my nerves when I do performance optimizations, You go into task, you're really motivated, I can do this. And then something bites you in the foot, and something bites you in the arm, and then, you can struggle. But there are ways to mitigate that, and this is basically the motivation of the talk. So I just showed you the first point, so why I'm here and why I submitted this talk. I want to introduce myself a little bit in the beginning, and then we take a dive into a more exploration of performance from an outside view. So in this chapter, I assume I get a binary, and it's slow. What do I do? Then I continue and start working with the source code. So that's performance inside out. And then at the end, I will dwell on how to create benchmarks and what pitfalls and what insights we can expect there. So my name is Peter Steinbach. I work for a company called Psyonix Computer Innovation GmbH. We are a software and consulting company founded more than 15 years ago in Dresden, Germany. So here's an excerpt of a map. So we're right here under the yellow pin in Berlin, and Dresden is 2 hours drive south of Berlin. So we have expertise in all branches of scientific computing, I would say. So data analysis, bioinformatics, image analysis, and high-performance computing, in short, HPC. And this is also the community where I come from. What I discovered and what you can discover every minute when you're here at the conference, everybody comes from his or her own community. And when they talk and when they exchange arguments, you will notice, I can assure you. So always take my claims with this in the back of your mind. One of our clients is the Max Planck Institute for Molecular Cell Biology and Genetics, and this is also where I'm based. There I fulfill the role of a scientific software engineer. So my task is to support our users on our high-performance computing cluster and get their applications running, try to help them, to parallelize them, get their jobs done quicker. And I also run small software projects related to performance in the more broader sense. So I do a lot of code porting to multi-threaded environment or to GPUs. The entire talk is open source. So I invite you to dial over to this GitHub page, and if you have any questions that I cannot answer or you feel that I didn't answer correctly, feel free to open an issue. I'm very happy if we can use this venue as a more open platform for any future discussions about the topic. Yeah. And of course, report any bugs that you find there as well. So before I begin with any of my discussion, I would like to stress that all of my slides assume that the code we are talking about provides the correct result. So for those of you who don't know, this is the Mars Climate Observer, satellite that was sent by ESA, end of the 90s. And at the end of its journey, I think 1.5 years or something, to Mars, what happened? It crashed. And the reason was, maybe some of you know, that there were 2 development teams. One used SI metrics, the other one didn't. And then you have a profound difference between pounds, seconds, and Newton seconds, right? And well, if the estimated distance to the surface is not correct, well, something will go wrong. Okay, and so I assume and I hope that you have tests. I work a lot with programmers in the high-performance computing community, and tests is something they know from the books, right? But not really often something that they do. So I urge you to have a suite of unit tests. Only with correct code you can really work to optimize the speed, because nobody wants fast code that produces a wrong result. Exactly. So let's get going. So I'll take you on a tour, one of my typical days at work, roughly. So most of the time it feels like this. Scientists are educated in academia to solve algorithmic problems. Typically they're getting taught tools to do that, and that's perfectly sound. But typically the problems that they solve, or they want to take the next step in terms of problem size, then these tools simply don't scale. And then I feel like this. I know how to basically operate a wheel, and then people are simply too busy to get going. In any case, so that's the typical situation. Once in a while I get a frantic email. What happened? What happened? It's slow all of a sudden. Yesterday it was fast. Today it's slow. What's going on? So yeah, so that's the typical situation. Fortunately, I'm working in a very productive environment, so we have a close way of communication, and then you sit down and try to find the cause. So in principle, what it feels like is that you have to mount a balloon and really get up into the air and find the street that has the most congestion, right? That's the task that I'm after now, because I don't want to touch the application at this moment. I just want to see and make sure that the hardware is not the problem or the source of the problem. So the tools that I use for this are the tools that everybody uses. The simple performance or power monitors. Here on the left-hand side, a tool called HOTSPOT, which many of you might know, and on the right-hand side, our beloved task manager. To just survey if nothing else is going on a specific node where some application is running slow, or slower than expected, I should say. The other tool that I use are benchmarks. Here I thought I'll just present something that I like to do a lot when people claim that the disk is at fault. So this is a small utility from the Unix command line called dd. And with this, you can write large files of no content. And that's very helpful if you want to check, for example, here, the top one, how fast is the built-in hard drive compared to RAM, right? And you can do this just to get a feeling, is everything working fine? Is the file system not corrupted in any way? Stuff like this. There are many more of these benchmarks that I like to run. I listed some of them here. You can go on forever and forever with this. But I have to say, it's very important that you have them in your stock and that you have a rough feeling of the machinery that you want to work on, what numbers it can provide. Because typically this helps you to actually guesstimate what the typical bottleneck of a given application can be. The other tool that I like to use a lot is PERF. So for those of you who don't know what PERF is, PERF comes with a Linux kernel. It's a small utility with which you can record sampling profiles of a given application. So here's the excerpt of how I do it. There was a series of great talks by Chandler Carruth on how to use that. So I can only invite you to check them out. I will keep the discussion here short. It's very lightweight. You don't need to expect any performance degradation of your application while you record the profile. That's very nice, because PERF uses hardware performance counters, or can use them, and does that by default. It can also use other data sources, but yeah, that's not what I want to discuss right now. So the typical output would be, if I want to render this on the command line directly, after you recorded your profile, you report it with this --SDO flag, and then it gives you a table of the most consuming functions and where they're in. So here in DD it would be a page fault, because actually DD doesn't do much. On Windows, there is a similar utility that you can also use for something I will discuss in a minute. It used to be called XPerf, now it's called something else. But I started looking into this for my cross-platform development, and it looks very promising for whole system profiles. So how does PERF work? So what PERF basically does, if you imagine this UML sequence diagram that I kidnapped here for my purposes, if you imagine a typical application that has a main function, and this main function then calls into some other compilation unit, maybe foo, and it calls here the init function there, and then continues getting the return value back, and then another call, etc., etc. And then in this submit function, there's maybe a loop that periodically calls this function called bus. So what does sampling profiling do? It simply does nothing else than this. So it simply calls an interrupt every given period of time, and at this period of time it records the call stack, so where your program counter is currently in, and then writes out for a given hardware counter the number of CPU cycles your program just consumed. So just for those of you who don't know sampling-based profiling, this is a rough rundown what it's all about. And the nice thing about this is it has very low overhead. And this is the reason why I like to use it. So as I said before, so after you recorded your profile, something that I like to do is visualize that in form of a flame graph. So this is something I will show in a second. So a flame graph is a simple visualization technique conceived by Brendan Craig, who is now working for Netflix. And it can be fed into, or can be based on data by PERF, by dtrace, SystemTap, and a lot of other profiling engines. And that's basically the nice thing about it. And it's really based on this, the collected counter samples and the call stacks for each sample. So this is a flame graph. So I thought it might be interesting to take the ETH miner. So that's the program that is used to mine the Ethereum cryptocurrency. Here I took the application that uses CUDA to actually run the mining onto GPUs, which are hooked into the system where this was taken. And to explain to you what this means, so note that on the x-axis, from left to right, this is not time. This is an alphabetical ordering of the call stack samples, nothing more. And this is done simply to help visualization, because if you do it by time, you get all kinds of colors in very, very tiny boxes, and you don't see anything. Okay? And on the y-axis, this is the depth in terms of the call stack. So here's the root node, and here's the process that I use, and then you descend in the call stack. And what you can already see, and this is a nice thing about this visualization, you can already see who consumes the most CPU cycles. Namely, there are two candidates, namely this encryption method here, SHA-3, 512, and the open no cancel. And if you're now motivated and want to try your luck, feel free to go now and try to accelerate this, but it will be against the idea of Ethereum. In any case, but this is just for illustration, to take a real-world application, so to speak. And here's the next illustration. So this is an actual use case from our cluster. So a user came to me with exactly a similar mail that I introduced to you earlier and said it's slow. So I recorded a trace, and what you see here, by the way, note that this is an SVG that I can browse, something I forgot to mention. So this is only CPU cycles, and what you see here, you again move from the bottom. There's the application that we were talking about, and then there's a lot of system calls about reading. And if you go further up, you always see these big blocks of raw spin lock. So this is a spinning block of the I/O system, in this case of a distributed file system inside our HPC cluster, which, as you can see, has a problem because the locks, they spin, but nothing happens. Now, based on this flame graph, we then went about and had a look, and indeed there was a hardware failure in one of the metadata servers that prevented the data from getting loaded. Of course, there are other monitoring tools that would have led me or us to the same conclusion eventually, but this is a really nice visualization that I can grasp very quickly, and which I like very much. So, yeah. So the bottom line of this section is that we have a myriad of tools that we can take to enter this balloon and really get up and get an overview of the lay of the land, what's going on, and where possible congestion may be located. Okay, so now let's be courageous and let's dive into this mess of code that potentially approaches us. So let's go inside. So now I have the freedom to play with the build system, play with the source code to actually find the hotspot. Now, this talk up until the middle is, or actually until the end, is about a collection of tools and a discussion of them. I can only say here at this point, profilers out there are really a lot. Some are good, some are bad. It really depends on your community, your use case, where you're working, which one you use. I can only make a very subjective selection that I like, and I had some criteria in terms of they don't need to cost anything, they need to come with a Linux system, so that I can use them very easily on a cluster. So always take this with a little bit of bias from my side. So let's get started. So this is something that typically comes with GCC and Clang. It's a tool called gprof. So gprof is nice because it's very easily injected into your build system. You just add one flag, namely the -pg flag. It's consistent between Clang and GCC. And then you run your application and it spits out a file called gmon.out, which you can then process and visualize on the command line. It's a simple text file. And here I took an example from Peter, who is there in the back, if I saw correctly, from Peter's book, Discovering Modern C++, about vector unrolling, where he illustrates various methods of unrolling. So what you can see here basically is that the runtime of this application is split up almost into 4 equal parts. And now you can potentially go and investigate the situation a little bit further. An alternative to this tool would be PERFTOOLS by Google. Another package, open source, that you can download and build. They took a different road. They offer you the possibility to render your results in, I don't know, 10 to 20 ways, either text-based in a table, as we just saw, or here in this visual representation. But the interpretation stays the same. So you have the system calling your process through libc, then your main function, and then the main function splits up its runtime in almost 4 equal parts. Here from a different run, so 70, 17%, and 15 and 14. So here it's really up to your taste. Here's another tool, very old-fashioned, I would say, in the Linux world, using Valgrind. Valgrind is rather invasive because it's based on like a pseudo-VM technology. So here, this would be an example where the runtime of your application is increased by a factor of 20. So it can take quite a long time for your application to run. So that's why it's not my preferred choice, to be honest. But what I like is the kcachegrind Qt GUI to actually interpret the results. This is very handy and is common in almost every distribution as far as I can tell. Something that has come up recently is an open source tool called HOTSPOT. I'm not sure if Miljan is in the room. I've never met him, but it's an open source tool sponsored by KDAP, if I understand correctly. And I think this has a very bright future, not only because it uses FLAMEGRAPHS, bias reminder, but also because it also started to introduce some other visualization techniques. Here is a simple timeline view of a multi-thread application. So you see basically if you then click on here, this is not an active apparently because it's a screenshot, you can color highlight, if I remember correctly, individual parts here for each thread. So this is again based on the PERF system. So this is in first instance GUI to interpret PERF call stacks, but it's a very nice one and it's relatively easy to install. So I really thank Miljan Wolf and KDAP for the investment here in this tool, and I hope it will continue. And of course, there are tons and tons of proprietary tools. Here I took the Intel Advisor 2017. From the documentation, it seems to be an excellent tool. And, but I have to say I would love to afford it. But of course it comes from the vendor of the CPU, so here I hope the gist of the hardware is inside this performance analyzer, and I know from colleagues that it's very helpful. And I could now probably name tons of other tools that probably provide similar or inferior capabilities, so it's really, there's really a lot of tools. So let's assume at this point that we have found a hotspot, so that we identify the function that caused performance regression. And now we have to do something about it. And this is actually, even if it's already after 24 minutes, the actual pitch of my talk. Because this is something that I feel goes wrong many, many times. Because of this, we enter the danger zone of mental models. What I mean by this is, I already experienced this a dozen times now here on the conference, when C++ developers talk to each other. Conversations typically go like this. Yeah, I mean, that's a simple problem here. You can use std variant. Oh, no, maybe std optional. Yeah, but the compiler will optimize this way, right? Yeah, this algorithm probably doesn't take too long on the CPU, does it? And then discussion goes on and on and on. And nobody actually sits down at some point, at least in my horizon, and actually measures this. And I think that's very dangerous. What people are doing, and I know very knowledgeable people, they use, for example, the Compiler Explorer, a great tool, I have to say. They're very happy that it's around, and I use it as well. But as Matt Gottwald said in his talk at CPPCon 2017, inspecting the assembly is not everything. You have to measure. There's no way around it. Because again, it's a mental model that you have of the hardware. And I can tell you, today's hardware is bloody complicated. In any ways, you can use PERF for that. You can use it for doing hardware exploration, mostly because it's very highly granular what kind of hardware events it can actually record. But PERF also comes with a ton of problems because it's tied to the Linux kernel. It's fixed to some point in time. So there's no guarantee that at the time PERF was built and your distribution built the kernel, that the hardware it's running on was actually present. So you can already see a mismatch, and you tend to come into big problems. And on top of this, performance counters are not always portable. So if you identify the performance counter that works on, let's say, Intel Sandy Bridge, there's no guarantee that the results you get are sound on a different hardware. There's a nice tool called OCPerf that tries to mitigate that. It also comes with a couple of other things. It's Python-based and also based on PERF. But something that I would like to show you is a tool called LIKWID by very knowledgeable people from Nuremberg and Erlangen. So this is something that I like to use because it's open source. It's basically a benchmarking suite and performance monitoring tool. It's Linux only because it comes from the HPC community. And it does, in principle, from a high level, at the core, nothing else than PERF. But it tries to give you, for example, this marker API where you can brace code snippets inside your code base, and then a LIKWID will only collect the counters from this region, if you want to say it. All right, so here's an example. I was told in the practice talks that this is rather hard to digest. I apologize, but it's a real-world use case that I just contrived a little bit for this talk. So this is it's a pseudo simulation, and it's also a pseudo talk by one of my clients. And he came to me and said, "So I have the simulation. It works well on my laptop, and it doesn't scale on the server. What's going on?" Now, so let's go through it real quick. So the structure of his code looks like this. So he has a structure that basically is supposed to encapsulate the behavior of little particles or filaments inside a geometric region. And they are characterized by a position and a momentum. And then they have a list of nearest neighbors that they interact with each other. And then this is a typical time-based simulation. You have some kind of vector that encapsulates the state of the world, so of this geometric volume and all particles in it. And typically these contain tons of these. And then you have a loop that actually does the time lapse. You do some update to this world, depending on how you structure it. You can do it here or later, it doesn't matter. And then very prominent in the HPC arena, use OpenMP to do the parallelization. By the way, range-based for loops are not supported by OpenMP, so this is something that won't work. In any case, so you loop over the world, and then for each item, you do some calculation over the list of nearest neighbors. Let's say this can be a distance, this can be a force, whatever. And then in his particular case, he had a threshold, and if the distance would be above the threshold, he would tamper with the item. So I thought, okay, what's going on here? There's multiple things that from my gut feeling could be going on and preventing this application from giving me good performance. One would be that you have rather large unpredictable jumps in memory, because this is nothing else here than an index list, and there's no guarantee that a local proximity of the individual particles in your 2D volume or 3D volume actually mean proximity in memory. Okay, so that could be bad for cache. And the other option would be this is a parallel application, and because he tampers with the individual memory here, because he removes something from this list of nearest neighbors, this code could be subject to false sharing. So what false sharing is, for those of you who never heard this paradigm or idiom or pattern, it's more a pattern, I would say. So false sharing applies to the fact that you have a parallel application, and then when your one thread loads a cache line, by coincidence, you have two kinds of items in this cache line. One that is needs to be mutated by another thread, and one that is read-only to the current thread. And what happens is basically that the cache coherency protocol will prevent, or will actually enforce, that this cache line will be loaded ever and ever. Because the cache coherency protocol from one thread to another needs to ensure that the memory always has a comparable state, right? And then this can basically lead to a bloody serialization of your parallel code. So, well, let's focus. So let's measure that. So here's a command line excerpt from LIKWID. LIKWID has a measurement group called false share. And what I did with the application here on the left-hand side, I ran it with one thread, and there you see the world is all good. You see that the memory that is subject to local false sharing is basically 0. But already if you go to 4 threads, you go boom. All of a sudden we have almost 3 gigabytes of memory that run into this problem. And something that I then always like to do is that compare this to a case where I know that there, by definition, cannot be any false sharing. That would be the stream benchmark. That's a data parallel application. So there is no, basically every thread works on memory regions which are independent of the memory region of the other thread. And here you see that there is basically nothing going on in that direction. So at this point, this was, for me, enough indication to actually talk again to the scientists, and then we sat down and tried to find a different algorithm for this basic problem. So the bottom line of this section is that there's excellent tools out there, even free ones, to find these hotspots. Once you found them, this is maybe something I didn't stress enough, it's always a good thing to talk to someone. Again, to not fall into this trap of mental models. This can be either a colleague or a rubber duck, like in Dennis Ritchie's case. For those of you who know that story. And then it's very important, and this is one of the things I would like to stress, that you create falsifiable hypotheses. That you come up with ideas what could be going on, and then you measure that, and either falsify them or confirm them. So benchmarks and how to create them. So again, we return to this abyss of actually trying to reach home. So faster code. Because that's why we actually come up with benchmarks. We want ultimately to find ways to run faster codes. And I don't know, Klaus, would you read it? Would you read what you said 2 years ago? Huh?
You mean a live reading?
Yes. I don't know. Can we have a microphone for Klaus, please? So this is to give you some context. So here we are now trying to come up with performant variants of an algorithm, right? And 2 years ago, after the keynote of Chandler Carruth, Klaus asked this question.
Okay, so guys that do know a lot about performance do a lot of manual unrolling, manual vectorization. Apparently they don't trust the compiler too much. What is your take on this?
Chandler answered, how do you define people who know a lot about performance? Serious question. So I work with Google's optimization team, who is responsible for making our C++ code run fast. And I have never seen them manually unroll a loop. Now, why I present this to you is because I want to stress there are always many sides to performance. Now, Klaus, and feel free to object, comes from a community of linear algebra, from HPC, and there we know from the library side, we know we want to solve the big problems, right? So we want to extract the maximum performance in terms of flops. Now, Chandler, and I invite Chandler, if he sees this on YouTube, to drop me a note or drop a comment and correct me, is working for Google. And my mental model of Google is, well, a lot of people, getting new machines is not a big deal. You have a lot of projects, you have a lot of developers, right? And their productivity is of much higher value than actual flops, because you simply have many people. You don't want convoluted code that actually, is unreadable because somebody 5 years ago thought, this is a real good optimization. We need to do this by hand, right? And then after this, he goes on about contributing to a compiler and that it's nice to have a compiler that you can change by submitting a pitch, and that's all good. But I wanted to stress the fact that performance is a very ambiguous term. Everybody understands something different, okay? So let's go through it, how I would actually envision to do a benchmark. And here with benchmark, I mean some kind of utility tool that helps me to see if a new idea about an algorithm in my production code base, so here I have a namespace, new ideas, and algorithm, is better than something that I already have. So it's not very complicated. Chrono is your friend here. You just brace this into 2 chrono statements, measure the time, and then you report the speed up. Off you go. Hello, my manager, 5x speed up. Can I get an increase in my salary? It's not always so easy. Something that I urge you to do, always check your result, right? As I said before, nobody wants wrong code that is fast. Taking the next step to this, do repetitions. A single measurement is not enough. It's really not enough, because here we're using a time measurement and our computers are stochastic beasts. So that means every time measurement in general is a non-deterministic measurement. So what you need to do repetitions that you can configure. Here I left that out, how many I do, just to illustrate my point. So you do a measurement of the timing, do some repetitions, and then at the end of the day, you report this mean result if you want it. Almost there, almost. So means are nice, but they obscure a very important aspect, namely they obscure the variation of your measurements. And this is a piece of information that you do need. Okay, we will see that in a moment. So one way you can approach this is simple. Again, you have your chrono measurements. You basically create a vector of timings, and then you measure the timing of each individual run of your algorithm, assuming here that the runtime of your algorithm is way beyond the uncertainty of your time measurement, of course. In that case, if you really have very, very, very tiny function calls that really don't take a lot of time, you have to devise something else. In any case, what I then suggest you to do is to store your results in a standardized file format, here being CSV. So what I do here, I open a file for those of you, and then I simply loop through the number of repetitions, and then I fill a couple of rows in a predefined way that I can then later on read in by not Excel, something else. We will come to this later. So you might wonder, why all this hassle, right? Why does it need to be so complicated? And the reason is this. I work with a lot of people that are not C++ developers, and they have one conception of C++. It's fast. Everything is blazing fast that just carries the name C++ on it. And we, as a community, we also have this idiom inside our head. Come on, just go to a talk. In the questions and answer session at the end, I can guarantee you there's at least one comment or question about performance. Right? This is one of the reasons why we chose it. And here in this bottom Stack Overflow comment, people actually make this explicit. So people expect something from C++, and so should we. And something that I would like to show you, even though this is from the high performance community, but it's very instructive. And I saw this in a lot of presentations from CPPCon over the years. So I'm also a reviewer for a couple of workshops at bigger conferences, and I can only confirm what they found. So this is the table. These people from Zurich, what they did, they took 3 conferences over 4 consecutive years and selected 10 papers at random of each. Okay? And what they then did, they wanted to check how the authors presented their results. Did they specify on which processor they ran their benchmarks? Did they specify the RAM size and the type, the compiler version, the flags, kernel and libraries used, etc., etc. And at the end, they even checked what kind of statistical reporting the authors used. And here comes the pain, at least for me. So many people rely on the mean or best and worst performance. So if you look at the total count, it's more than half of the papers. But if it actually goes down to the measure of variation of each measurement, you really see a big drop. All right? So you go down from 51, so only 17 of these 51 potentially also report the variation of their results. Now, for those of you who are not so familiar with statistics, what do I mean? So here's a screenshot of a web service called QuickBench, which is, by the way, a great inception that I just learned recently about. So on the left-hand side, you define your benchmarks. On the right-hand side, you click a button, and then it displays you these nice graphs. Now here, everybody would agree that, I mean, it's quite clear which variant of this code is actually faster, right? Now let's make a small Gedankenexperiment. Let's assume the situation would be like this. So we have error bars or uncertainties attached to the mean values, and they extend, they even overlap. Would you still think the left is better than the right? There's some indication, yes, but would you be fine to deploy this to all your users in a new version? I personally, with my background, I would not be so happy. It's strong that these 2 distributions do not match, but my point is that these variances tell you a story. Okay? They tell you a story, something about your measurement. And the same authors of the paper that I just showed you, they then visualized this here. So they did a very famous benchmark in the HPC community called HPL, and they actually plotted the individual runtimes. And what you see here, you see a very nice distribution, which, by the way, is not Gaussian. An assumption that is very inherent to many, many statistical techniques. So from here, I learned something. I learned a lot about my measurement, right? And this has to be reflected in our discussion of performance, I believe. Now the question is obvious, can this be automated? The answer is yes. There's a nice library, open source library by Google called Benchmark. And it's written in C++ 11 and 03. It supports multi-threaded applications. It compiles your binaries, including a simple but very powerful command line interface. It's relatively easy to set up, and let's just dive in. For the sake of example, I took 2 code bits by Matt Goldbold from his talk at CPVCon. So his main question was, are range-based for loops faster than integer-based ones? Right, simple thing. I hope you can see it. So this is an integer-based trip count for loop. Very simple thing that has been around forever and ever. And then here's our beloved for range for loop. Okay. So the question is one better than the other? If you want to check this with benchmark, you do it in the following. So here's our implementation of this integer-based for loop. So I simply hand over a pointer and the length of the data that is behind it, and then loop through it, and then I reduce the content into this double called value, and I return it. Range-based for loop, same thing. I have to do it, as this is C++ 11, I have to do something with the type, but that's more cosmetics to make the compiler happy, and then I do effectively the same thing. And if I then want to register this as a benchmark here on the right-hand side, you define a freestanding static function. The only requirement here from the framework is that you have to receive this benchmark state object. Then you set up your input data that you want to work on, And then you simply have a for loop over this state, because the framework controls how many iterations you have. And then you actually perform your operation. The nice thing is, and this was alluded to in a lot of talks in the past, that the framework comes with a small trick to prevent the optimizer from actually optimizing this call away. Because obviously you don't use the end result at some point beyond. And then you register your benchmark, and you do the same thing with the other implementation. And at the end, you have a macro, as far as I understand, to actually put in the main function. Very simple. How does it look? So that's the output. If you run this on the command line, it gives you a small tabular output, the different two versions of your benchmark here, the average time that each iteration took, and then how many iterations were conceived. The nice thing is that this framework actually checks if CPU scaling is enabled on your on this machine, which can skew your results, as you might know. And so that's very nice, I think. You can also do this with more input data sizes. Here, the setup is similar. So again, you define, here we do it with a templated benchmark, retrieve the range item from state, and then create our input values based on that. And then the rest is the same as above. And now what we can do by means of this arc function, we can actually provide a range of values that we all want to test with our benchmarks here. Okay? Right. And I do this for both of the types that I want to check. I want to see if it's dependent on the type, whether this kind of for loop is performing the same. So you can do this, and you can even have multiple arguments for each benchmark. So my workflow with this kind of stuff is the following. So first, I of course have to build the benchmark, compile it, maybe even with varying flags if I want to run and inspect the results. And typically, if I want to repeat this or want to present this to others, I use our Markdown to actually compile a report. That's a very nice thing to do, because there you can use simple Markdown and interleave it with statistical analysis, where our CSV formatted input data comes into play again. And then I can even show this right away to my boss, because it's nicely formatted and contains some results. So here's the output that you would get just on the command line. And I hope you can see that it basically takes all of my arcs and sweeps it through. So I can traverse the memory hierarchy on my processor, and then gives me the timings. And it does that for both variants of ints and floats, and for the range-based for loop. Now, question is, what is the outcome? So that's the result. Here I took the mean and standard deviation as computed by benchmark, so this library, and what you basically can see is that math's completely right. There's no difference as we expected between float and int. There's more variability, which I believe comes down to singular instructions that need to be different between the two code variants. So what I invite you to do is to actually do this at home if you want, and submit an issue to my repo if you want, and see if you can reproduce this. Because this is also another aspect which currently is called the in silico crisis in many, many academic domains, namely that results that are obtained on computers are very hard to reproduce. And I would like this situation to change. So I invite you, if you want to play around also with my code, file an issue, and there we go. So there are other frameworks that do similar things. Not sure if the authors are in the audience. So here's my take on them. I did a quick comparison of them. On the left-hand side, you see the GitHub project identification with the user and the project name. This column indicates how many GitHub stars this project already obtained, and then my pros and cons. So just going through this real quick. This first library, Hayai, is based on Google Test, which is nice because you can interleave these tests for sanity inside your benchmarks, of course outside the time measurement. But from my point of view, it has a couple of shortcomings because, for example, it doesn't support CSV output by default as far as I could tell. And what I also don't like is that it's by default prints out maximum, minimum, and the means of the runtimes, which is something I would actually never do. But many people still do. Celero, also a very interesting project because there this library works in a way that you always have to define a baseline, and any code variants are always compared to this baseline, which can be very handy. No CSV output by default as well. Means are reported, that's not so nice. No news was the most confusing of the four to me because I didn't even get what the right repo is. That's why I have 49 to 194 here, because there are apparently two repos that have current head. I didn't get it. But the thing is, and that's why I mentioned it, it has a super statistical summary. This author actually, I mean, he even gives you confidence intervals on your mean and variance estimations. Thumbs up. I mean, very nice. But it's a little bit confusing, the whole repo structure and everything. And then we have Google Benchmark. No dependencies, that's nice, very feature-rich in terms of what it needs to be done. Very well received in the community. And the only thing that I don't like here is that it also reports means by default. And as I said before, it would be nice if it would be means plus variance. So the question is, where do I stop? If I have a given problem that I want to solve, where do I stop optimizing? Well, at this point, after we already conceived the first or wrote the first benchmarks, it's actually too late. In a sense that you should have an idea where you want to stop in the beginning. Is it some kind of minimal time you want to run within? Do you only want to support some specific kind of hardware, some specific kind of libraries, which could be a potential bottleneck, etc., etc. The last thing that I want to introduce you is a way of predicting the performance of applications called a so-called roofline plot. A roofline plot serves me at least very well in terms of a mental model that you can actually measure. So what this is, it's simply a graph where on the x-axis you plot the operational intensity of your implementation, so the number of flops you invest per byte read or stored. And on the y-axis you actually plot performance of your application. So there's basically very important two lines, namely this diagonal line or linear function, if we want to call it, until this ridge, and then this constant line here. And this is also the reason why it's called roofline. So inside this model, there's a clear separation between work and traffic because everything that is below this ridge, so in this region, is bound by memory bandwidth. And everything that is beyond this ridge, so in this region, is bound by flops performance. And there are ways to actually map this to other metrics, which was done in the community a lot of times. And I also want to stress that this roofline model for predicting performance is not without problems, but it solves for many cases with a lot of interesting insights. So here there's an excerpt from a publication where people started off with two manual implementations of their problem. I don't want to even go into details, and then switch to using performance optimized libraries, namely Atlas here and the MKL. And up to here, they didn't do any multi-threading. But then at some point, they switched that and went to a parallel implementation. And you can see that here, for example, in this specific example, the MKL even reaches the maximum what is actually theoretically possible on this very machine. So that is sometimes nice, but I warn you to draw any general conclusion based on this. Okay? It's really, the nice thing about roofline is it's always specific to a problem. Okay? Even though the graph will stay the same, but you always have to repeat the calculation on what you enter here. And if you think that the roofline behavior, this roofline ridge, is something academic that you never ever see in reality, I have something of my from one of my own benchmarks that I published this year. And there you see a roofline, but inverted. So this is a benchmark of FFTs that are computed either on the CPU in red or on the GPU in blue. And you basically see this very same behavior. There's some flops limited, so work limited region, and then you have a ridge, and then you're only limited by memory bandwidth. Okay? So bottom line of this section is that your requirements to your product, be it an academic, open source, or proprietary product, basically give you the guiding light in this dungeon of performance optimization. Reproducible ensemble-based benchmarks for me are the key to actually very robust insights, and I would strongly encourage you to pursue the same path as I would like to. And that brings me to my summary. My talk had 3 sections, and maybe the 3 takeaways are: if you run into performance problems, first take a balloon, get an overview, or if not, then notice the problem. Then falsify the rubber duck in a sense that you actually come up with falsifiable hypotheses that you can profile and check for. And then at the last step, try to survive the dungeon with automated ensemble-based testing and benchmarks. So here are my final words. For me, C++, not only for my personal opinion, but also in the community, not even only inside of C++, but also beyond, is a language considered fast. And I strongly would like to invite you to discuss with me this claim that I think the community need to live up to this standard and have robust and reproducible performance numbers. And with this, I'd like to thank you for your attention. So I guess time for questions, as I understand, if there are any.
So, hi Peter.
Klaus.
Thank you very much. I feel very honored to be included in your talk. So this was quite nice. So, but I'm also very grateful that you picked on this topic again, because I feel that Chandler dismissed this very, very quickly, far too quickly. Yeah? I'm not aware of any compiler that's doing loop unrolling perfectly. And so I'm truly grateful. Thank you very much.
You're welcome. You're welcome.
Can you elaborate on the colors in the flame graph? Because to me, at first glance, they didn't make any sense.
Yeah. For this reason, I chose a profile that doesn't make any sense. So there are presets for the colors, but here I think there's no reason really in the one that I chose. But there are in the Perl or the tools, which are basically Perl scripts in the FlameGraph GitHub repo. There are different presets. Mostly they are meant for a situation where you, for example, want to profile Java applications, so that you can differentiate actual Java calls to the actual C or C++ implementation of the JVM and all that kind of stuff. In my case, sometimes I use them, but often I don't, because they are not so important. I mean, depending on your taste, I guess. You're welcome.
Thank you, Peter, for using me as well in your talk. And I want to comment on Klaus' comment that so compilers are getting much better in unrolling loops, and in unrolling one-dimensional loops, they are already usually better than hand unrolling. And my experience is if you have 2 or 3 nested loops, the hand unrolling is usually still faster, or if you have to use multiple temporary variables, the compiler hesitates to do so. So there are cases where hand unrolling is better, but as you said, you have to measure this first, and often cases you have the Pareto principle that 90% of the time is spent in less than 10% of the code. So it's not worth to tune your whole application, but focus on some very performance intensive kernels and tune them and leave the remainder as it is and make the code as simple as possible, and don't screw up your code in the hopes that you win a few nanoseconds.
Yes. Up here, up front.
Sorry, it's not tightly connected to your talk, but I think even though it is a good standpoint that we as a community need to live up to the standard in terms of performance and reproducibility of these numbers, but also the standard contains some deficiencies which really prohibits to achieve the best possible performance. And in case you are interested what some of those are, I will do a lightning talk tomorrow, so it's
Cool.
shameful.
Cool. Thanks for sharing that. Good. Well, again, then we have a coffee break, right?